Hello and welcome to lecture number 5 of this series and the third one on molecular recognition. Today's perfume is by a French company called Caron and it is called Pour un homme, which means for a man, and it's a very beautiful, very simple, at least in appearance, lavender, very high quality lavender. And the reason I like it is because, first of all, it smells great. And secondly, my father used to wear it when I was a child. So for me, this is the smell of freshly shaven daddy. And it really is pour un homme. One thing I find amusing about this is that they do, Caron seems to be doing years. So this is the 2014 vintage lavender. I love the idea that there would be different years for perfumes like there are for wine. So today's lecture will be about, again, molecular recognition. We've seen in the last lecture that the shape hypothesis, while completely plausible, reasonable in principle, did not have much predictive power when it came to actually predicting the smell of a molecule. Now, why is it plausible? Well, it's plausible and reasonable to suppose that it's shape because many things in biology work by shape. For example, when you get vaccinated against a disease, they inject you with some part of the virus or the bacterium, and you make antibodies, and the antibodies have the exact right shape to stick to the bits of the bacterium and make them less toxic, less dangerous, or prevent them from infecting cells or some such thing. So this idea of lock and key, which dates back to the early 20th century, or actually late 19th, with the work of Paul Ehrlich, is very common in biology and completely reasonable. The fact is, it may or may not apply to smell, and this is what we're trying to figure out in these lectures. So, one question one might ask is, what is the alternative theory? What possible other explanation than lock and key, after all, could there be? And the answer is molecular vibrations. So where does the idea of molecular vibrations being involved in smell actually come from? Well, originally it came from a really rather philosophical concept, which was that we have the sense of color vision and the sense of hearing, and they're both related to vibrations. In the case of vision, it's the frequency of the light which determines the color of something, at least in a very simple-minded model. In hearing, it's of course the frequency of the compressional waves in the air which hit your eardrum, get transported into the cochlea, which is a frequency analyzer, and then the little nerve cells in the cochlea, each region responds to a different frequency, and that goes to your brain and gets analyzed as a sound. So if you have a philosophical bent of mind, as many people did in the late 19th century or mid-19th century, you might say, oh, wouldn't it be wonderful if the sense of smell were also a vibrational sense, also sensing the vibrations of molecules. Now, of course, it costs nothing, or not much anyway, to propose this sort of idea, and it has a certain attractiveness in terms of unity of nature, etc., which is something that people in the Romantic era and later were very fond of. The notion that all of nature was built according to a common principle or principles. So one of the first people to propose this was a man called Ogle, who was a medic in the 1870s, I believe, who wrote a treatise on the senses and mentioned that possibly the vibrations of smell, the molecules were responsible for their odor. Now, we didn't know much about chemistry, the molecules at the time. We certainly didn't know a lot about the vibrations of molecules, but that didn't stop him from proposing this rather vague idea. Now, then in about 1925, something revolutionary happened, which is that C.V. Raman, who was an extremely distinguished, one of many extremely distinguished physicists from India, invented a particular type of optical machine called a Raman spectrometer. And I won't go into the details of how a Raman spectrometer actually works, but what I can tell you is it measures the vibrations of molecules. And in a later lecture, I will show you what the vibrations look like. But let me do it with my hands for the moment. A molecule is made up of atoms connected by bonds, and the bonds are elastic, or springs, and the atoms are masses. And you can imagine that this thing can vibrate in a variety of different ways, like these two atoms could go like this, or the whole thing could pulse, and so on and so forth. And that's exactly how it happens. What makes them vibrate? Well, it depends. Up to a certain energy of the vibration, if I can just explain what that energy is. If you have two very light atoms connected by a very stiff bond, the frequency of the vibration will be very high. In the same way that a small violin will play a higher note than a double bass. So it's a question of masses and stiffness. And the higher the vibration, the higher the energy of the vibration. In other words, the higher the pitch, the more energy that vibration has. And under normal circumstances, you can only make things vibrate by thermal energy. And thermal energy only goes up to a particular energy, which, depending on how you express it in units, we will just use, from now on, I'll use wave numbers, and I'll explain what they are later. But roughly speaking, the spectrum of molecules is between 0 and 4,000 wave numbers. And thermal energy is 200 and something wave numbers. So all the molecular vibrations which are above the 250 wave numbers will not be excited, will not happen because of thermal energy. It's actually not a sharp boundary. So you can go up to 500, 600, 700. They'll still be occasionally excited. But then when you get to higher, like 1,500, 2,000, it'll never happen. Okay, so those are the molecular vibrations. Now, so what does a spectroscope do for you? Well, a spectroscope is a wonderful machine to identify the component atoms of a molecule. If you're a chemist working with an infrared or a Raman spectroscope, the infrared and Raman work on similar principles. The infrared came later. The first one was the Raman. If you're working with a spectroscope like that, someone hands you a molecule and says, tell me what this molecule is. Well, what do? You put it in your machine, you press the button, and it gives you a spectrum. And the spectrum might, for example, have a peak at 1800 wave numbers, or a peak at 2100 wave numbers, or a peak at 25, or a peak at 3000, etc. From that, just without any further information, you can deduce that if it has an 1800, chances are it has a C double bond O. If it has a 2150, chances are it's a C triple bond N. If it has a 2600, it's an S single bond H. And if it has further up, you get to OH stretch and NH stretch and so on. So, in other words, a spectroscope identifies functional groups very easily. And that is already a very striking feature, since our nose can do exactly that. Now, what about in the lower region of the spectrum? Well, typically when you put a molecule that has, let's say, that has carbons arranged in some pattern plus a functional group, what you get is the functional group vibration, and then you get the vibrations of the skeletal part, of the carbons and the hydrogens. And they form a complicated pattern, which is called the fingerprint region. It's called the fingerprint because it's literally unique to each molecular architecture. So, can you take the fingerprint spectrum, which is made up of many, many different vibrations all superimposed on each other because they're slightly blurred? Can you take that fingerprint and somehow invert it and figure out the structure of the molecule? No, you can't. However, if you have measured that molecule before and you already have a fingerprint region for that molecule that you have identified by synthesis or some other way, then when you compare your unknown to that guy, if they match, you know that's the one, because fingerprint regions are unique. So imagine you're a chemist in the 1920s and you're interested in smell. And you've heard about Raman spectroscopy and you're actually using it in everyday practice in the lab. It stands to reason that you would notice the similarity between the sense of smell and the spectroscope. On the one hand, it detects functional groups with great ease by their very specific vibrations in the upper range. And on the other hand, it can tell different carbon skeletons apart very easily in the fingerprint region in the lower range. And the first person to notice that was a British chemist called Malcolm Dyson, who was an extremely interesting person. He had been, in the First World War, he'd been in the trenches in France, and he had been gassed twice, in fact. I believe by phosgene, which is an extremely unpleasant war gas, which has the smell of hay. It's a rather pleasant smell. So Dyson proposed this theory in several papers, and it was, I think, pretty much ignored, although people were unquestionably aware of it. It didn't have much traction for reasons that I will explain. After Dyson stopped working on it, the whole thing went pretty much dormant for 2 or 3 decades. And it was revived by an extraordinary man, Robert Wright, who was a chemist in Western Canada. And Wright was both a chemist and also he worked with insects. He was an entomologist, and he was interested in attractants for insects and that sort of thing. And he proposed, again, that smell was to do with vibrations. And at that point, he, being a logical mind and a very good scientist, he concluded from first principles that since the vibrations that were actually happening at room temperature were the only ones below thermal energy, so let's say between 0 and, 500 wave numbers, let's say, for the purpose of the argument, that only those vibrations would matter to smell. Now this was a little bit tricky because Bob Wright, who, when you look at his portrait, is my idea of a scientist. He's an extraordinary looking man. Bob Wright was one of the few people who had in his lab what's called a microwave spectrometer, which is like the Raman or infrared, but at a lower energy, lower pitch of vibrations. There are not many microwave spectrometers around, so he was in a great position to look at the spectrum from 0 to, say, 300 wave numbers, because he had the machine to do that, and no one else had. And so people were not really in a position to say, well, you've got it wrong, this vibration doesn't fit, etc., because they didn't have the instrument to contradict him. Now, when I first looked at this, I thought this was highly unconvincing because of a simple reason. When you have a molecule which is thermally excited by heat, and you're going to probe, you're going to have it attached to a receptor that's also being thermally excited by heat. How is the information going to travel from one to the other? In other words, how is the receptor going to know that this vibration that's happening to it is due to the molecule and not to the receptor itself? I can only measure thermal agitation if the thing that I am measuring is hotter than the instrument that I'm measuring it with. It's practically impossible to imagine a system where you have two bodies at the same temperature and one can measure the molecular motions of the other. And I don't think Bob Wright ever really overcame this objection, and in particular, he never proposed a mechanism by which this could happen, even though there are very sophisticated second-order type mechanisms that potentially could do this, but it never got to that point. And his theory was briefly fashionable in the 60s, and then basically disappeared from the scene. Now, the fourth scientist who plays a very important role in this is a chemist also, of course, as usual, from the University of Kansas in Manhattan, Kansas, which is known as the Small Apple, as opposed to the Big Apple, which would be Manhattan, New York. And I met Clifton Malone, and he, in the early 80s, he became interested in this because a student of his, he was an analytical chemist, so his job was identifying molecules. He used spectroscopes all the time. And one of his students said to him, "How come our nose is so much better than our instruments at detecting small amounts of chemicals?" Basically, the analytical chemist's job is you first have to concentrate the thing, and then you have to identify it with the spectral or whatever, or magnetic resonance methods and so on. But the nose, you can just put this under my nose, linalool, lavender. So Clifton Malone told me that he was really angry at the fact that he, as an analytical chemist, was less good than his own nose. And so he started studying this. And he made some very important discoveries. The main one of which was that if you change the vibrations of a molecule without changing its shape, insects would no longer recognize it. So how do you do that? Well, you take a molecule, for example, cineol, which is the smell of bay leaves, and cockroaches, for example, hate cineol. In fact, I think that's why bay leaves have cineol, to keep insects away. So you have an interesting experiment that you can do. You could take the cineol and you replace all the hydrogens in it by a heavy hydrogen, an isotope of hydrogen called deuterium. What happens is the shape's pretty much the same, but all the vibrations are being changed because the heavy hydrogen atoms change the spectrum. They change every vibration because the masses get bigger. So he did this. He took some deuterated cineol, and he had cockroaches in a box, and he had 2 cups like this put down in the box, dark paper cups. And when you turn on the light, the cockroaches go under the cups because they hate being in the light, so they go in darkness. And he put cineol under one of the cups and deuterated cineol, in other words, heavy cineol, under the other cup. Gets the cockroaches in, turns on the light, and all the cockroaches go to the deuterated cineol, meaning they're not repelled by it. The normal cineol is a repellent, so they don't go in that cup. They go to the other one. So this is absolutely amazing. It means the cockroaches can actually smell the presence of deuterium. And so he tried to publish this in various journals, as one does as a scientist. You have to at some point submit your research to a journal, and they all turned him down. So he published, in the end, this work in a very obscure publication in a Congress proceedings. It was held in Greece, I think, in 82 or thereabouts. And this was basically, he was actually, I think, rather disappointed by the reaction of his fellow scientists to this new information. And so gradually he sort of gave up on it.